So we'll wrap things up today with an example that's somewhat simpler than the last one. Here you can see that we have a binary counter that's composed of 4 flip-flops, where each one of the flip-flops is set to toggle mode, and the output of each flip-flop serves as the clock signal for the next one. This is the classic configuration of the binary counter composed of toggle flip-flops, and what we're going to find is that it's not too hard to figure out what the waveform is going to look like. Here I'm going to go ahead and clarify that this is the, I can't seem to get that to work properly. This is the clock signal, okay? And then I know that Q0, this is flip-flop number 0, flip-flop number 1, number 2, and number 3. Flip-flop number 0 is going to come directly from the clock. And so every time that there's an active edge on the clock, there's going to be a transition in flip-flop number 0. And so this is not too hard to do. It's a little bit tedious, but we're finding that the frequency of flip-flop number 0's output is going to be 1/2 the frequency of the original clock signal. Now the output of Q0 is going to be serving as the clock signal for flip-flop number 1. So now I'm looking for active falling edges on that clock signal. So I'm identifying those active falling edges here. And those will now serve to identify the transition points for Q1. So Q1 is going to transition only when there's an active edge on Q0's output. And so notice that the frequency of Q1 is 1/2 that of Q0, which makes it 1/4 that of the original clock signal. Now Q1 is going to be serving as the clock signal for Q2, so I'm going to identify the falling points here, and that will be the places where an active transition happens on Q2. And let's see. Yep, it's just off the edge of the screen where the last transition is going to occur. So now we can see that we've divided the frequency by half yet again. And there's only going to be one active edge here on Q3. So Q3 is going to do this, and it's going to continue on. So if we were to look at the values of the Qs, we would find that this is 0, 0, 0, 0. Then we would have 0, 0, 0, 1. And then we would have 0, 0, 1, 0, 0, 0, 1, 1, or 0, 1, 2, 3. And then we can keep going. 0, 1, 0, 0, that's a 4. 0, 1, 0, 1 is a 5, and so on. It'll continue up to 15. I think 15 is just off the right side of the screen, and then it will cycle back to 0 again. So this shows that it does, in fact, give us the binary counter that we're looking for, and that each one of the flip-flops is going to have half the frequency of the previous flip-flop. Let's do a couple of quick design problems. I have a clock signal operating at 40.96 megahertz. So this is going to be a square wave. You want to decrease that frequency to 10,000 hertz, 10 kilohertz. How many flip-flops are you going to need? So I'll have 40.96 megahertz divided by, make sure that's a capital M, divide this by 10 kilohertz. When I do this, I'm going to get 4,096. Now I can take the base 2 log of 4,096, and I'm going to end up with 12. And so it is, in fact, 12 flip-flops. Or I can ask myself, 2 to the what power is equal to 4,096, which, by the way, is exactly the same question that's being asked by what is the base 2 log of 4,096. Well, I know that 4,096 is going to be 4 times 1,024. I know that this is going to need 10, a power of 10. This one's going to need a power of 2. So therefore, n is equal to 10 plus 2, which is 12. So in either way that you solve it, you're going to end up with 12 flip-flops. A clock signal is operating at 100 megahertz. It is applied to a binary counter with 22 flip-flops. What will be the frequency of the output of the last flip-flop? Okay, so we have 2 to the 22. I'm going to do that one on my handy calculator here, and I'm going to end up with a number that is 4194304 or what we would probably call 4 megabytes, 4 million. We can see that, by the way, 2 to the 20th, 2 to the 20th times 2 to the second. This is going to be about 1 million times 4, which is about 4 million. But the precise answer is shown here. So 100 megahertz divided by 4194304. I'm going to invert that first number and I'm going to multiply it by 100 times 10 to the 6th. And I end up with 23.8. 23.84 hertz is going to be the frequency of that last signal. So it's a very, very high frequency signal, but it's being divided by a factor of 4 million. And the final answer then is around about 24 hertz is going to be the output frequency of that signal.